graphs that are also third-iterated clique graphs.
Okay, thank you. As the title suggests, this will be a presentation about some classes of iterated clique graphs and how they are related. So let us start with a brief introduction before showing the main problem. The basic concept is the concept of clique, which is a maximal set of pairwise adjacent vertices of a graph. We define the clique graph of a graph G or K of G as the graph whose vertices are all the cliques of the graph, and two of them are adjacent when the intersection is non-empty. And the function K that assigns to each graph in its clique graph is usually called the clique operator. So for example, let's consider this graph G. In that case, the clique graph will be this graph, and for example, the clique C6 and clique C8 share the vertex H, so we must have them adjacent in the clique graph. Another related concept is the concept of iterated clique graph. So given a natural number n, the nth iterated clique graph is obtained by applying the clique operator successively n times to the graph G, and it is usually denoted by k to the n of G. So let's again consider this graph. We already know what the clique graph is. This clique graph has 5 cliques, and all of these cliques have the vertex C3 because that is a universal vertex. So the second iterated clique graph, or k squared of G, is just the complete graph on 5 vertices. The notation k to the n of G is used to denote the image by k to the n of all the graphs, and is usually called the class of nth iterated clique graphs. So this presentation is motivated basically by this question. Given a natural number n, we are interested in knowing whether k to the n of G is equal to k to the n plus 1 of G. This is a really difficult question, and so far what we only know is that k of G is different from k squared of G, and to prove this inequality we should use octahedral graphs. Given a number n equal to 3 or larger, the octahedral graph O n has 2 times n vertices, which are the first n natural numbers and their primes. And it has all possible edges except the ones of the form I prime, where I is a number which ranges from 1 to n. So for example, if we consider O3, it is just the Laplace graph, and if we consider its clique graph, which is here, it can be identified as O4 because we can make these vertices play the role of 1, 2, 3, and 4, and these vertices play the role of 1 prime, 2 prime, 3 prime, and 4 prime. And octahedral graphs are useful because O4 is a graph that is in k of G minus k squared of G. One idea of the proof is as follows. We can break the proof into 2 main steps. In the first step, we show that for every graph G such that the graph is equal to O4, then O3 must be an induced subgraph of G. And when we know that structure for G, then we have to prove that that graph G is not a clique graph. When it was proven that the clique graph of O3, which is O4, is a graph in k of G minus k squared of G, it was promising to think that the iterated clique graphs of O3 could give some other counterexamples to prove that some other classes of iterated clique graphs were different. In that case, it should be true that k squared of O3 is a graph in k squared of G minus k cubed of G. When trying to prove this, one approach could be trying to replicate those two steps to prove that O4 is a graph in k of G minus k squared of G. It is possible to perform the first step because we have this result that says that k squared of O3 is 08. In fact, something that I did not say before is that the clique graph of an octahedral graph is always another octahedral graph. So we have that k squared of O3 is equal to 08 at every graph G, such that the clique graph is equal to 08 has O4 as an induced subgraph. But well, this was possible to do, but this was impossible. So when this was impossible to do, one starts to suspect that this is not true. So to continue, we now consider line graphs. Recall that the line graph of a graph G, or shaft L of G, is a graph whose vertices are the edges of G, and two of them are adjacent, if and only if they have a common vertex as an endpoint. So for example, if we consider the complete graph on 4 vertices, its line graph is shaft O3 because K4 has 6 edges, and for each edge there is another one that does not share any vertex with it. We have that k squared of O3 is equal to k cubed of the line graph of O3. So this tells us that our initial assumption that k squared, the k cubed of O3 will give us a counterexample of a graph in k squared of G minus k cubed of G. That was not true. This equality, it is very easy to prove using a computer. When Miguel and I tried to prove it by hand, it was clear that it was very useful to have each clique of O3 be a triangle. That is, every clique has size 3. Thanks to noting that detail, it was possible to conclude with this theorem that says that if G is a graph whose all its cliques have size 3, then k squared of G is equal to k cubed of the line graph of G. To prove this, we have to understand the structure of the clique graph of a line graph. Line graphs have 2 types of cliques. Some cliques consist of edges of a triangle, and some cliques consist of edges that meet at some central vertex. Let us call these cliques class A, and these cliques class B. So we have that 2 class A cliques are adjacent when the 2 corresponding triangles share an edge. One class A clique and a class B clique are adjacent when the central vertex of the class B clique is one of the vertices of the triangle, and 2 class B cliques are adjacent when the central vertices B and W are adjacent in the original graph G. So for example, if we have this graph G, this is the clique graph of the line graph, where the blue vertices correspond to class A cliques and the 4 vertices correspond to class B cliques. And these red vertices can be seen as vertices of the original graph G. And now let us consider 2 more graphs. The graph G prime that is obtained from K of L of G by adding all the vertices of G that were missing here, and another graph H, which is constructed by considering each edge that is contained in more than one clique and for that edge we will add a new vertex and we will make it adjacent to the vertices of that edge. So it turns out that k squared of g is equal to k cubed of L of g by this chain of equalities. K squared of g is equal to k squared of h, which is equal to k squared of g prime, and we finally get to k cubed of L of g. So another way to express this result is by saying that the composition of L and k is an operator that preserves k squared when we are restricted to the class of graphs of the theorem, that is the graphs that have size cliques with size 3. So we have always that k squared of these graphs is contained on k cubed of g. As an easy corollary of this theorem, we have that when for each graph g such that every clique has size at most 3, now we allow smaller cliques. It is also true that k squared of g is a graph in k cubed of g. So, for example, if we have this graph, what we have to do is just add simplicial vertices to each clique that does not have size 3. And now we have a new graph where all the cliques have size 3. Because these vertices that we added are simplicial, the second iterated graph does not change, so we can apply the previous theorem to this new graph. When we consider graphs with larger cliques, everything becomes completely different, because if we just consider the most simple of those graphs, which is K4, its line graph is O3, as we just saw before. K squared of this graph, since this is a complete graph, just consists of one vertex. And on the other side, K cubed of O3 is an octahedral graph. So we have two completely different graphs that show that the result is not true anymore. So we could try to think of other operations to apply to graphs with 4 vertices to try to extend the results. And it could help to consider the graph G prime of the construction of the proof theorem. We can see this graph G prime as a graph obtained by adding for each clique one vertex, making them adjacent to the vertices of the clique, and 2 of these new vertices are adjacent when the corresponding cliques share one edge. If we consider this as an operation to try to preserve k squared, well, unfortunately it will not work for all graphs. For example, for this graph it doesn't work because if we apply the operation, we obtain this graph, and k squared of g has just 2 vertices consisting of these 2 pairs of cliques, while g prime has 3 vertices in k squared of g prime. For this graph g star, there is a similar problem. But if we discard these 2 graphs in the sense that if we have a graph H such that G and G star are not induced subgraphs, and every true clique of that graph H, those 2 cliques have an intersection, then the intersection has no more than 2 vertices, then it is possible to obtain an extension theorem. In this case, we have again that k squared of g is a graph in k cubed of g. But, well, this is a limited result because those counterexamples. So, if we want to prove that both graphs have k squared of g in k cubed of g, we should try to think about more operations. Another operation consists of adding vertices of k squared of g, that is cliques of cliques, instead of just adding cliques of vertices as the previous construction. And to explain that construction, let us do it with an example. For example, suppose that we have this graph. What we will do is to take one edge at a time, for example this one, The first step will consist of considering all the cliques that contain that edge, which in this case is just this clique. And for that clique that we obtain, we consider all the cliques that contain it, which in this case are all the cliques of the graph, which are these new vertices. What we do in that case is taking the edge, taking the cliques obtained, and make all those vertices pairwise adjacent. And when we finish with that construction, applying that position for each edge, we obtain this new graph. Well, this operation behaves very well and proves that k squared of some graph is also in k cubed of g for many instances, but we again have counterexamples, for example this one. So one more attempt to generalize this is a very similar construction, which will have the same steps as before, but if we here consider edges, we will not have now that restriction anymore. What we will do now is not only consider edges, we are not allowed to consider sets of pairwise adjacent vertices of G. And for that set of pairwise adjacent vertices, we again repeat the same operations. We take the cliques that contain that set of pairwise adjacent vertices, and we consider the cliques of cliques that contain those cliques that we obtained in the previous step. What is good about that is that this operation always gives a clique graph. So if this clique graph has the same k squared of the original graph, then we can conclude that k squared of the original graph is in k cubed. And for example, when we have the graph 04, and we take the edges as a cover, as set covering all the edges of the graph, the construction doesn't work. But if we apply the same operation to edge cover consisting of a Helly family, then this operation gives indeed a new graph such that k squared is just equal to k squared of 04. So if we follow this approach, when we have a graph G, what we must try to do is to try to find a family F of pairwise adjacent sets of pairwise adjacent vertices which cover all the edges, and trying to find that family in a way that it is appropriate to get a new graph such that k squared of G is still the same. So as we see in this example, for some family it could fail, but perhaps we can find some other family where it works. So some concluding remarks, we could say that the methods that I showed here allow to discard several graphs as counterexample graphs in k squared of G minus k cubed of G. So we are in a much better situation as before, but there is a long way to go because there are still too many graphs for which we don't know what happens. So there is much more to do about this topic. That's all.
So, many thanks. While we start the next presentation, we still have time for a question. No, we do have time for a quick question, but we don't have a presentation here. We changed the computer. Yeah.